All right, so let's take a look. I'm going to do a little bit of application of some of these integrals today, and then going to do a little bit of definite integration with some trig. Be kind of our goal today. So we've got a train that's moving along a straight track with an acceleration of t over 10 minus 3 meters per second squared. If the initial velocity of the train is 45 meters per second, determine the total distance traveled in the first minute, all right? And so when we take a look at this, what we're doing is we've got to work our way back to the original problem. So we're given the second derivative. I'm going to rewrite this. I'm going to write this as the 1/10 t minus 3. It's a little bit easier, I think. So this is the acceleration. So if I were to work backwards, I'm going to add 1 up there, so it'd be t squared. I'm going to divide by that 2, all right, minus 3. I'm going to add a t. I'm going to add a c. So here in my blue, this would be my velocity equation, all right. So the velocity, I'm going to rewrite it a little bit simpler. That would be 1/20th t squared minus 3t plus c. And it tells me that my initial velocity is 45 meters per second. So right here, all right, if I were to plug a 0 in for t, 0 in for the t, then that's going to give me the 45. So my exact, very accurate equation would be 1/20th t squared minus 3t plus 45. Okay. Now, not quite there yet because I'm trying to find the total distance traveled in the first minute of this problem. All right. And so what I'm going to do is I'm going to work backwards again, all right, and find my my displacement function. So if I were to do this, my displacement function here, all right, I'm going to take the antiderivative of that. So this would be t cubed. This would be 1 over 20, and then it would be 1 over 3 minus 3t squared. There's going to be a 2 there, plus 45t, sorry, and then plus c. Kind of ran out of room over there as we go. All right. So if I do this, I'm going to rewrite just so I can see this a little bit better. This would be 1 over 3 times 20 would be 60. T cubed minus 3 halves t squared plus 45t plus c. Now, earlier we did this, we went backwards and we were able to find the exact problem, but I don't have c, all right? And so c would be my starting location. Do I need to know the starting location to be able to determine the total distance traveled? It might be helpful, but I don't necessarily need to do that because I'm going to end up subtracting my distances here as we go. All right. Take a look here. I'm going to plug in, since we're going for seconds here, we're going to go for 1 minute, so don't be confused by that. I'm going to evaluate this from 0 seconds to 60 seconds is what I'm going to do. All right. Since I'm doing a definite integral, we've seen that our c value disappears. So I'm going to plug the 60 in. So 1/60th, I'm going to go 60 cubed minus 3 halves. I'm going to go 60 squared plus 45 times 60. I'm going to go plus c. So I'm evaluating that on that part minus, now I'm going to plug the 0 in. Well, the 0 is kind of nice. So if I plug the 0 in, I basically would just have c. It would be 0 plus 0 plus 0 plus c. And those c's are going to cancel. So if I were to do this, let's see if we can work out of this and find this exact answer. All right. So 60 cubed, that's a pretty good number, but if you notice, I have a 60 there and a 60 there, so one of those is going to cancel. So this is really just 60 squared, all right? So 60 times 60 would be 3600, all right? That's the same thing here. It's 3600, but I'm multiplying it by negative 3/2. So that's going to be a negative 5,400 is what that is. And then plus, I'm going to multiply that together. And so that's going to be 2,700 plus C. All right. So if I add all this up, I'm having 3,600 minus that plus that. That's going to give me 900 meters is what that's going to do. Okay. Now, I'm going 900 meters. 900 meters would be approximate of like 9 football fields. And I'm doing that in a minute. All right. Doesn't seem like that super fast, especially when our initial velocity was 45 meters per second. And 45 meters per second, that's moving pretty fast. So something's not quite right in this problem. All right. If you were to take a look at this velocity, if I were to set it equal to 0, which we've done before, and if I were to try to solve this, I can factor out a t, and I'm going to factor out a 1/20th as well. So when I factor that out, I'm going to be left with t. I'm going to have to take that 3, and I'm going to have to divide it by 1/20th. And if I do that, I believe that 60 is what that is. All right. And so, let's see here, 1/20th. Excuse me, I'm going to have to go 3 divided by 1/20th. Okay. 3 divided by 1/20th. And that should give me 60. Now, what I'm doing here is I'm looking for where the velocity is equal to 0, because the velocity is equal to 0 at 0. All right. Actually, that's not correct. I didn't do that. I'm sorry. Now I need to go back. I forgot my 45 in there. So I need to have my 45 in there. Let's go to the calculator. That's a little bit more complicated here. Now, and so I'm going to go to calculator and let's go figure this in the calculator. So if I were to do that, I'm going to go menu and I'm going to add a graph. And I have control division 1/20th. I'm going to say x squared minus 3x plus 45. If I do that, that's going to be a little bit more helpful. Hopefully, I'm going to go menu. I'm going to go zoom. I'm going to go Windows settings, and I need to see the first 60 seconds. So let's go like maybe 90 seconds, whatever. Okay. And so when I look here, I've got something going on here. So at this location, menu, let's go find, I'm going to analyze the graph, and I'm going to go find a 0. So if I do that, I've got a 0 at 30, and I got, that's it through that graph, okay? And so what I have here, this helps me to understand what's taking place. I have a negative velocity, it's slowing down, and then it's going back forward, all right? So my velocities are changing. And so did the train actually change direction? Did it go back the other way? The answer to that is no, because underneath, if I went underneath, then that would be going the other direction. That'd be a negative velocity, which would mean I'm going back to the left, all right? And so, but because it slowed down and stopped and then started taking off again, then I can be confident in the fact that this 900 that we got a while ago, it is correct, all right? So it's just not going super fast. It's braking, it stopped, then it's starting to pick back up speed again. And so it didn't go quite as far as what we had thought in that first minute or whatever. So at 30 seconds, it was at rest and it took back off again. So that helps me to explain that a little bit better there. There's another concept in there that we're going to talk about too that I was about to check on that, but I was able to verify it that way. All right. The marginal cost of producing X items per week is given by the derivative of cost, which is the marginal cost, and there's that derivative, per item, and provided that I'm going from 0 to 120 items. The initial cost before sales start are $185. Find the total cost of producing 100 items per day, all right? And so I need to write this equation. So if I were to do this, I am going to go work backwards. I'm going to do the antiderivative or the integral for this right here. And so if I were to do that, I would get 2.15x minus, it's going to go x squared, so that means I'm going to have to divide that by 2, so 0.01 x squared, plus this is going to have to go to a cube, so 0.0012 x cubed, and then plus c. Now, on this one, it says the initial cost before production sales start are $185. So if I were to plug a 0 there, 0 there, 0 there, I'd have $185 as my initial cost. Now, I don't really like the way that this is structured. Let me rewrite this in standard form. So that would be 0.0012 x cubed minus 0.01 x squared plus 2.15x plus 185. So there's my cost equation, all right? It says find the total cost of producing 100 items per day, all right? Total cost of producing 100 items per day. So now what I'm going to do is I'm going to go take that 100 and go plug that in. So if I were to plug 100 in there, 100 in there, 100 in there. Well, 100 cubed would be a 1 with 6 zeros behind it, which means I would move the decimal 6 places. 1, 2, 3, 4, 5, 6. So there's that one. If I do 100 squared, that's 100 times 100, so it's got 4 zeros. So 1, 2, and then 2 more zeros. This is multiplied by 100, so that's 2 zeros, and plus that. So without a calculator, you can type in the calculator, that's fine. I'm just doing that by hand here. So I've got 900, and then I've got these two things put together. So if I were to put that together, I got 400. So it looks like I got 1,300 there. Okay. Now, that's one way to do this problem. I'm going to show you another way to do this problem here as well. All right. If I use my technology to do this, what we're doing on this problem right here is if we were to start off at 0 and we were to go to 100, then if I start at 0, it should be $185. And if I go to 100, what I'm doing is I'm finding the difference there, the variable difference from producing 0 items to producing 100 items, all right? So that's another application for these integrals, all right? That would be that additional cost underneath that line, all right? And so if I were to type this into the calculator, I'm going to go, let me go doc, and let's go insert, and I'm going to insert just a calculator. I'm going to go menu, and I'm going to go calculus, and I'm going to go numerical integral. We did this the other day. 0 items on that one, 100 items there, 2.15 minus 0.02x. I'm going to double check that real quick. The original 0.0, and then plus 0.0036, 3 zeros there, 36x squared. All right, so plus 0.00036x squared dx. So if I were to do that, I get $235 is what I get there. That's the difference there. Well, what I have to do is I've got to compare that with what I started with. I started with $185. So if I were to add $185, then that should match. Now I got 420 there, So I'm a little bit off. I must have typed something in incorrectly, and let me double check my work. 2 point there, and let's see here. I'm off. Double checking, sorry. Let me look at my notes real quick. And so if I was doing that, I must have done an antiderivative wrong. I believe I did. I found it right here. So 420 is correct. And so what we did here is correct. I had done a miscalculation doing it the other way. Let me show you real quick. So this had 3 zeros here. This should have had 3 zeros here. All right. So this should have had 3 zeros here, which means that would have been 120 instead of 1200. So 120 minus 100 would be $20 there. This was 400. So that would have given me the 420. Sorry, one little decimal place. Change that up. And so we could do this either way. We could take it back all the way there. We can let our technology help us with that, doing the definite integral, knowing that the difference between what I started with and what I ended with was $235, but I started with 185, and so I can add that together and I can have the cost of 100. And you could do that with whatever amount of units that you want to produce, up to 120, because that was my domain. Okay? All right. Let's go again. So let's try one more of these type problems here. All right. Metal tube has a cross section as shown below. So this is, cut this pipe in half. The outer radius is 4 centimeters and the inner radius is 2. So from here to here is 2. And from here to there is 4, all right? Within the tube, water is maintained at a temperature of 100 degrees Celsius. That's boiling. That's like 212 Fahrenheit, so that's pretty hot. Within the metal temperature drops from the inside to the outside at this rate. So as the water flowing through here goes through the pipe, it does get a little cooler. It gets cooler at this rate of change. All right. So what I want to do is I'm going to do the integral of -10 over x, and I'm going to evaluate that. That pipe is from 2 centimeters to 4 centimeters, so that's the difference that it has a chance. It's not going to go from 0 to 4 because 0 to 2 is still water. All right, and so it's only going through that pipe from 2 to 4, and then dx. So I'm going to evaluate this here. And so if I were to do this by hand, I would probably split this like we've been doing in class. All right, take that -10, take it out front, and then if I were to do that, then I'm taking the antiderivative or the integral of 1 over x, which is natural log. So my antiderivative is -10 natural log of x plus c. I'm going to plug the 4 in, so -10 natural log of 4, not worried about the c, minus -10 natural log of 2. The two negatives there are going to make a positive, and I don't really know what that value is, so I'm going to go to my calculator to assist me on that. And so I'm going to go -10 natural log of 4 plus 10 natural log of 2. And if I get that, I get negative 6.39 degrees. That's in Celsius. So negative 6.93 degrees Celsius. That's my answer. Or is it? All right. Think through it real quick. Since this is the integral, this is the change in temperature from the inside to the outside. So the temperature has dropped 6.93 degrees. So if it was at 100 degrees Celsius, it dropped that. So now we're at what, 93.07 degrees Celsius. We can convert that if we'd like, but that's gonna still be pretty hot, all right? Probably would not be good to touch. And so if I have this pipe going through like a warehouse or something like that, I'm probably gonna make sure that I put something around it, to keep people away from it, because I think it's probably still too hot to do, to have anybody touch it or anybody lean up against it and get burned, okay? If I were to do this problem in the calculator, we'll see what we just did there. We can go menu, we can go calculus, numerical integral. We're going from 2 to 4. The problem, the original problem was negative 10 over x dx. And if you notice, we get that same negative 9.3. And if I did 100 plus that value that we just had, then that gives me the 93.07 that we were referring to. Okay. All right. Let's keep going. So there's some application there. Just wanted to show you some of that. I'm gonna do a couple problems here on some trig and some definite integrals on trig. So on this problem right here, if I were to have the integral of the sine of x dx, all right, and I'm going to go from 0, which is right here, to 2 pi, which is right there. So I'm going to evaluate that there. Okay. So if I were to do this, the representation that we've done in the notes, they've kind of split this, all right? I'm going to do the antiderivative of this, and they're only doing this first part right here. So we're going to go from 0 to pi. So if I were to do that, all right, I can work through this process. I can say sine, the antiderivative of sine is negative cosine plus c. If I were to evaluate this now, I could go negative cosine of pi minus negative cosine of 0. If you think about the unit circle, yes, we're back on that. Pi is right here. That's got a value of 1. All right? But it's negative. So this is negative 1. So this right here is negative 1 times negative would make that a positive 1. Cosine is right here. That would be 1. So this is 1. And I have the 2 negatives there, so 1. So 1 plus 1 would be 2. So the value of that is 2. So I did my definite integral to show that. If I were to do this right here, if I was same thing, but now I'm going to find this area. Now I'm going from pi to 2 pi. Same definite integral. Excuse me, same integral. It's negative cosine of x. I'll go plug that in. And so I'm going to plug in negative cosine of 2 pi minus negative cosine of pi. So if I were to do that, those two are both positives. This right here, cosine of 2 pi, like we did on the graph a while ago, that's there, that's 1, but it's a negative out front, so negative 1. Plus cosine of pi is right there, that's also negative 1. So this value right here has a value of negative 2. Now we talked about shapes earlier, a couple days ago. If we did this and we said, okay, well, what if we put the two together? If this is 2 and this is negative 2, they offset each other because one's above, one's below, and the integral for the whole thing would be 0. Now, I'm going to go on and discuss this just real quick on this, just so when we talk about it, we can see it. All right. when we do the integral, it gets us what's referred to as displacement. It's a keyword that we've seen some in physics, all right? Think about the train example that we did a while ago. From the starting point to the ending point, that is displacement. Now, this is a little bit different because when I have a positive integral up here, that means I'm going, say, to the right, all right? If I've got a negative right here, it means I'm going to the left, all right? And so the location where I'm at is in the exact same spot. And so we have like no displacement. That's what this is showing here, all right? If I were to have fallen asleep while this happened, all right, it would have looked like the particle or the object of the train would not have moved, all right? And so that's what's taking place here. So one concept, another application for an integral, and it is the area underneath the curve, but it also tells me displacement. We can use it to find distance. We'll talk about that soon. All right? I'm going to do just a couple more antiderivatives for you real quick. I'm not going to spend a lot of time here. We've done a few of these. So let's take a look. So if we're to do this one here, this is kind of a unique graph. I've got e dx plus 1 over x. It gives me this graph that you have shown here, all right? We're going to evaluate this from 1 to 2, which would be from 1 to here, and then I want to find the area of that curve. So if I were to do this, I would do the antiderivative. Obviously, if you had your calculator, you could just plug it straight in and get the answer, all right? We'll do the antiderivative. So antiderivative of e dx is e dx. Antiderivative of 1 over x is natural log of x plus c. Now I'm going to go evaluate that. So I'm going to go e to the second plus natural log of 2 plus c minus e to the 1 plus natural log of 1 plus c. Now, again, we talked about this the other day. The c's will cancel. But also, if I've got a log or a natural log of 1, that's 0, so I don't need that. And so what I end up having here is I have e squared plus natural log of 2, and then minus that e right there. That would be my non-calculated answer. All right? I could plug that in and get a decimal if I'd like, but if I got my calculator, I'm probably not doing all this work here. I'm probably just taking that and I'm going to go plug that into the calculator. Okay, I want to do one last one here. This is the last one I'm going to end on the day. I'm going to skip that one in the middle. I'm going to go talk about this one. All right, on this one right here, it says find the area of the region enclosed by the x-axis. So if I kind of read this, this is worded slightly different. And so if I'm going to enclose with the x-axis, the line x equals 1, the line x equals 6, and the natural log, excuse me, not natural log, but e to the x, try again, 1 over x. It's that rational function that would look like this. So the part that is bounded or enclosed by the x-axis, the 1, the 6, and that value is this area right there. So when I'm building my integral, the curve that's on top is 1 over x. My boundaries are from 1 to 6 dx. And now I can go through here and I can undo this one. Now this one works out really well. The hardest part of this one is just kind of setting it up, knowing where the pieces go. This again is natural log of x plus c. And I can plug in 6 there. I can plug in a 1 there, but again, we saw that a while ago, that's 0. So natural log of 6 is my answer. Okay? All right, I'm going to finish there, let you guys, you can work on page 566 is our homework. All right, and we will continue this conversation on Monday.